x1 to xn plus 1 that we took, उसमें if we take xn plus 1 is equal to 0, then our last n comma n entry 0 to the power 0 नहीं हो जाएगा?
All are 0 because if the last guy will be something bigger than 0.
No, so in the last column we are getting ones in the last column because
No. We are getting ones only when the length of A is less than equal to. So we are getting. So if the length of A is less than n, then the last entry you pad it is 0 for A. So A n plus 1 will be 0.
Right, Professor. So when we take when we take xn plus 1 equal to 0 as well, so हमारा last entry will be xn plus 1 to the power an plus 1, which will be 0 to the power 0.
Right. But I'm saying that in this situation, so this is fine this is what we get for here, when length of A is less than. If length of lambda is bigger than n, we will get something here. In that case, there will be xn plus 1 raised per something. Then putting a 0 will kill the entire. That's why one has to have n large enough to capture the length of lambda. Okay, so now we want to. So I've really not done everything very nicely over here. You would, if you were doing an algebra thing, you would be actually proving very nicely, that there is an isomorphism and so on. So there is a sequence and there's an isomorphism, so that it doesn't really matter if you have more than a sufficiently large number of variables. But anyway, so let's not get into that. Now we want to, what I want to do for the remainder of the day, and for, maybe we'll finish early. We want to do show you some of the theorems, the combinatoric theorems. So for that, we want to write Ferrer's diagrams in this way, because the book does it, and I'm not sort of strictly following everything in the book, but you will see a lot of stuff like this. And as per McDonald, you see, if you want the other way, then you see upside down in a mirror, and all theorems will work. So normally the theorems are like this. So McDonald is English, he's British, and the French guys who have worked on it. So McDonald uses this, other guys use this, most partition theorists use this, most algebraic combinatorialists use this, and we can go up and down. It's not a big deal. So anyway, so the French have done significant work in this area, and that is the reason why we follow this. So in E lambda, so this is something like this, and you put some numbers there. It's called a Young tableau. So a Young tableau is something where you put numbers in this kind of thing. And E lambda is, we saw that it's got strictly increasing numbers in various rows, in rows. So we had this kind of example, I think, something like this. And this was allowed. Something like this was allowed. So this was okay, and this corresponded to x1 raised power 2, x2 square, x3, and x5. Right? So this was not allowed, right? We had strictly increasing in rows and columns. No, this was okay. This was E1, E2, E3. This was E1 times E2 into E3, and this is what this monomial corresponded to. So let T be a filling of a Young diagram. i.e. a tableau um, with, so, and I represent by xt, so maybe I should say let f1t be number of ones filled in, so the frequency of ones, f2t be the number of twos in the t, and so on. So fk is the frequency of k in t. The frequency like we had in a partition, a similar deal. Then this guy I will use to represent x1 to the f1, x2 to the f2, and so on. So what am I saying? I'm counting the number of ones and writing x1 square, counting number of twos, there's two of them, so x2 square, x3, x5. So that's a number. And E lambda can then be written as x to the t, where t is a tableau with shape lambda, and row um, strict um, filling of lambda. And row strict means increasing strictly, increasing in rows. So it's a generating function of row strict tableau of shape lambda. So let's do an example. So let's take lambda equal to something about 3133. So this is lambda, and let me see that what is the coefficient of. I want to see what is the coefficient of x1 square, x2, x4 cube, x6. Okay, so x4 is coming three times. It has to come in all the three rows. So in the first row, we have to start with an x4, right? And there is 1, 2, 3, 4, and 3, 7. So x4 cannot come uh, here because I need x1 also. So x1 is the smallest, so I need two x1s. So I have to have x1, x1 here. And then the possibilities are that I could have x2 and x6 here, and x4 and no, I need an x6 here. So I can do a x4 here. This is a possibility. Or I can have x1. This is fixed. I mean, I can't do anything about x4, x4 over here. And I can have x2 and x4 here, and x4 and x6. So we saw if I have an x4 here and an x6 here, then there's a problem with putting an x4 here. So I have to have x2 and x4. So there are exactly two such tableau. So coefficient of this is exactly going to be 2 in this thing. So, and we can verify that because it's easy. So this is x1 plus x2 plus x3 plus x4. 1, 2, 3, 4, 5, 6, 7. Well, it's not so easy to verify. Let's leave the verification. So it's kind of obvious that this will happen. So yeah, so this we are aware of. This we did last time. Let's see what we can do for h lambda. So this was obvious that it has to increase in rows and it has to be strictly increasing because elementary symmetric function is the type where you we don't have any repetition. So it has to strictly increase. Okay, so let's do h lambda. How does one do h lambda? So again, same thing. You do the what is my example? Let's do the simplest possible example. So let me do h2 of x1, x2. So here you have a box of these two guys, and you can, uh, well, h2 involves x1 square, x2 square, and x1, x2. So it's a, if you multiply everything, you're going to get a homogeneous thing. So basically, you allowed all these guys. So it's h2 and h lambda similarly will be a product of all these guys. So h lambda x is summation of x to the t, and t is a tableau filling with the uh, weekly increasing in rows. So weekly increasing means non-decreasing. So i.e. non-decreasing. So here you allowed whatever you allowed one. So basically, what's happening is that there is a you are taking all partitions which are sort of fitting into this lambda one bigger than equal to lambda two less than. So right. So h lambda is of course with of shape lambda. So again, if you have something like this, so you'll have at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You'll have to have 11 variables and you fill them up in even this is allowed. If you do this, you'll get x raised per 11, x1 raised per 11. And if you fill twos, all twos, you will get x2 to the 11. And if you have some ones, which have to be like this, so you can get, if there is just one, then you get x1, x2 raised per 10. So whatever the filling, as long as it's weekly increasing, you will get a homogeneous symmetric function. And this is how does it. And then the number you count. So as many as it gets, that's the number of ways of doing. So again, it's rather obvious. The book has about 15, 20 pages of proof for these kind of things. If you're interested, please look at it. So what I'm most interested is in shoot functions because this is really painful to calculate the determinant definition. So a semi-standard filling of a tableau of shape lambda is a filling of the Young diagram of lambda in which entries are strictly uh, increasing from bottom to top and weakly increasing from left to right. And a standard tableau when both strictly increasing in rows and columns. So when you're going from top to bottom, then they are strictly decreasing. So if you're top to bottom, then you increase like this, right? And if you're bottom to top, you increase like this. So it's the same thing. I mean, it's not a the whichever way you keep the tableau, actually, the math remains the same. So let's do an example. And the point is, the point, first let me say what the point is. Say, sure function is a number of x raised per t for t which are semi-standard tableaus. So let's do an example. So length of lambda is 3. So we want xn, let's take x3 to be equal to x1, x2, x3. And let's just see what, so we are fitting 1, 2, 3 into 3 columns. So strictly increasing if it's strictly increasing, it has to have this. And the shape is 1, 1, 2. So this can be 1 and 2. I'm not making the boxes. It can be 1 and 3 and 2 and 3. This has to strictly increase. This can be weakly increasing. Right? So these are all the possibilities. So should lambda of x3 is equal to x1 square, x2, x3. So 2 of 1s, 2 of 2s, and 1 of 3 plus x1 square, x2, x3 square plus x1, x2 square, x3 square. And then I thought that what we do is let's calculate the other way. So I started like this. So we have this 2 to 1. So what do we have got? So we have lambda I plus n minus j. Basically, we have to make a thing. So it's x1. So lambda 1 is 2. So 2 plus n is 3 minus 1. So you get 4. Then 2 plus 3 minus 2, you get 1 less 3. And then uh, you get 2. Okay, so x2 is also 2. So I is, sorry, lambda I is 2 plus n minus j. N minus j is n is 3 minus 1. Oh, there's something wrong here, isn't it? Yeah, there's nothing wrong. So 4, it's 2, 3, it's 2, 2. And then third one is x3. And x3 there is difference. Something 1 plus n minus j, right? 1 plus 2. So 3. x3, 2, and x3, 1. So you want to take this and you want to divide it by the random one. Anyway, it became very complicated. So after 2 pages, I gave up. I did work it out on the computer and I checked it, and it worked out nicely. But this is a lot more complicated if you just try it. So this is a lot easier way of doing it. Of course, to prove that this is the same which we are avoiding right now, we are not doing that. Okay, so but going by this, we have not seen what sure functions are for one race per k. So let's just look at this guy. So what we are doing is that we have this long partition 1111, and we have a filling which is strictly increasing, right? So I mean, the simplest example is when, first of all, when k is bigger than n, that means if I put x1 to xn, I'll run out of xi's. So at some point, I'll have to put 0. So x s1k of xn is 0. If k is equal to n, then I'll put 1, 2, so on up till k. So I'll get ek. And in fact, if k is less than equal to n, I will still get ek. So this means that s1 to the k xn is equal to e raised per k for k less than equal to n. Is that clear? I mean, I'm putting it, it is column strict. So I have to do one, 1, 2, 3, so on. And vice versa, if I do sk of xn, then I should get hk, because here it's not column strict. So here it is what we did earlier. So uh, this is also easy. So here you can do things like this. Your weekly increasing. So you take the shape of k over here, and again for k bigger than n, it's 0, and k less than n, less than equal to n, it is hk. So this is a special case which is not so easy to determine. Um, okay, is that clear?
Yes, Professor.
I think it's just you and me now, is it?
Yes, Professor. Pratik texted me saying his Wi-Fi died, so we'll
Ah,
have to do the recordings.
so it doesn't matter. We might have a recording. So let's try some more examples of S21. So if you just have X1 in it, and here is the shape. So you start with putting a 1 here, you can put a 1 here, and then you have to put a 2 here. So this is not there, X2 is not there, so you'll get 0. So this will be 0. So when there is no X2, uh, then you get 0. So the minimum you need is the number of parts. Okay, so now this is possible, this is possible. I mean, you can't have 2 and 2. You have to have 1 and 2. So this is fixed. and this chap is this
Can be
chap.
one or two bits. Yeah.
So we'll have x1, x2, 1, x square is x1 square x2 plus x1 x2 square. So that's okay. Let's try one more. So here we have this guy is allowed. This is allowed. Then let me just want to make the boxes. So this is this guy. Then I can have two here instead of, uh, then I can have three here. So these three are there. Then 1 and 3 is possible. And then I can have one here. With 1 and 3, I can have these three possibilities. Then the other possibility is 2 and 3. I can't have one here because it's weakly increasing. So these are the only possibilities. So there are 1, 2, 3, 4, 5, 6, 7, 8 terms. And we have S21 of x3 is x1 square x2 plus x1 x2 square. This will give me x1 x2 x3 plus x1 square x cube plus another one of this. Then this is x1 x3 cube plus x2 square x3. And so just two of these, is it? Plus x2 x3 square. So now the thing to be noted is, suppose we write it in terms of m lambda. So the biggest term is this guy, okay, x1 square x2. So this is equal to m to 1. And then there are two of these chaps, m11. Right? So, I mean, in general, S lambda of x can be written in terms of, uh, so this I think is the definition I have written it, right? Yeah. In general, if you want to write it in terms of m mu, then whatever the coefficient lambda mu is, this c lambda mu is called the, I think it's called the Koska numbers, but anyway, it's the number of fillings of lambda um, by, so here you calculate the frequency of ones in mu. F mu, F1 mu ones, F2 mu twos, and so on. So what are we saying? We are saying that mu is given by 2, 1. So you want number of fillings which have two ones and 1, 2. And so, for example, here you have two fillings. This corresponds to two fillings of this shape. So of this shape, there were two fillings which had 1, 2, 3 in it, which is this guy and this guy. So these are the two fillings where 1, 1, 1, 1, 1, 2, and 1, 3 come. And that will give you the coefficient of M111. So these guys, the fillings, number of ones, number of twos, number of threes are determined by this mu. So number of ones is 1 here, number of twos is 1 here. So how many fillings are there? Exactly one filling. With this filling, you take all the monomial symmetric functions. Very, very, very simple and easy formula to remember. So if you want to write down, as per monomial symmetric, that's very easy to. So Fn mu is n's. So many n's, so many n's. I hope this is clear, right? So if mu is in old-fashioned notation, 1 raised per f1, 2 raised per f2, n raised per fn, then so many ones, so many twos, so many uh, n's should fill this shape lambda, and then that's the. Okay. Then there is this identity. So this is one identity. This is one theorem. So I'm not proving these things. I'm just indicating to you what they mean. Uh, then there is one which is Jacobi 2D formula or identities. So point to be noted is that Jacobi actually considered symmetric these two functions uh, before Schur himself. Okay, but Schur did a lot of representation theory work with them. So what does this identity say? It says that S lambda of x1 through xn is the determinant of a matrix H lambda I minus I plus j. And there is a similar one for E's. So E lambda I prime meaning the transpose minus I plus j. So let's do our simple example x1, x2. Right, so here lambda is S2 1 says so lambda is equal to 2 bigger than equal to 1. So lambda 1 is 2 minus I, that's 1 plus I, so this is H2. Then H of uh, this is H3, and uh, this is I is 2 here, and so it's 1 minus 1 H0. Sorry, and H1. So this is H1, H2 minus H0, H3. This I think one can do by hand. Um, Let me see. So H2, H1 is X1 plus X2 times H2 is X1 square plus X2 square plus X1 X2. And uh, you're subtracting this by H0, which is 1, and H3 is X1 cube plus X2 cube plus X1 square X2 and X1 X2 square. So yeah, this guy on the left is X1 cube plus X1 X2 square plus X1 square X2 plus X2 X1 square plus X2 cube plus X1 X2 square minus this chap. And let's just cancel it directly here. Um, this gets cancelled. This gets cancelled. X1 square X2, one of them gets cancelled. X1 X2 square. So this gives you these two terms. So this is what we got for S21, this guy, x1 square x2. So this works. These are called Jacobi 2D identities. The proofs are a little complicated, not that very tough. And there's one more formula I want to show you, and then we'll stop. So this is called the hook length formula. So what is a hook? You have this, suppose you have this partition, and suppose so you consider a cell. So suppose this is a cell, this guy, this is cell X. And what you do is you consider the hook. So you count all these guys. Okay. Idea. So you count, suppose this is the cell, you count all these boxes and you count this box. So 1, 2, 3, 4, 5. So the hook of this cell X is 5. So if this is X, X is the cell, then this is the hook. So let's do a. So what is the hook for this chap? Or this chap? There's nothing on the left, nothing on top, so it's 1. Here, uh, 1, 2, 3. Here, it's just nothing on the right, nothing on top, so it's 1. Here, it's 1, 2, 3, 4, 5. Here, it's 1, 2, 3. And here it's 1. So these are the hooks of each cell. Okay. And the formula says that the formula, again, we won't do the proof. The number of standard tableau of shape, this is a remarkable formula. Lambda is n factorial divided by the hooks of cells where x belongs to the lambda. This means that the x is a cell in the Young diagram. Of lambda.
Essentially, multiplying each of the hooks, right? Like each of the hook lengths.
Uh,
We are in the denominator. We are just multiplying each of the hook lengths, right?
right. So just to do this example, what is the number of standard tableau of this shape? Which is 3. So example, the number of standard tableau of shape this thing. So number of tableau of standard tableau. Standard, by standard I mean things which are increasing always. Okay. So not semi-standard. Semi-standard was weekly increasing on the left. But let's just do this. So there are 6 of them. And then you just do 1 into 3 into 1 into 5 into 3 into 1. So this goes to 6 into 5 into 4 into 3 into 2. And then 5 gets cancelled. 3 gets cancelled. And then another 3. So that's 4 into 4, 16. So we know already that there are 16. So this is a remarkable formula again. So, I mean, the point of most of math is to figure out formulas in some sense. And things get very tough to do. But in this area, of course, there is one more which I am not mentioning, but I'll just mention briefly that there are these other types of results. So there are called Peary rules. So what you do is you multiply ek by, if you multiply s lambda by ek and you write it in terms of s mu, then what are the coefficients? How do you do that? And more generally, if you multiply S lambda and S mu, and then you write, so this is a partition of lambda, this is, absolute value of lambda and something. Then you can write it in terms of some coefficients. I mean, these form a basis, so you can write in from. So these guys come from what are called the Littlewood Richardson LRU. So all these objects are, positive, and they come up with, they have some combinatorial meaning. So lot of combinatorics is hidden. Okay, so that brings me to the end of the thing. As a class representative, you're you're the only one who's survived this course, I can say.